5. This one's pretty short and sweet. It kind of ties into what we were doing with exponential growth, but now we're going to look at a logistic model. And so it's going to, basically we're starting with a differential equation. It could look like this or like this. And basically the solution, and again, we could use separation of variables, rearrange all of that stuff to prove it. The proof is in your book in section 7.5 if you want to take a look on how they get from here to here. But if you see a differential equation that looks like this, the solution is always a log function or a logistic model that looks like this, okay? And so basically, we can kind of use that to pick out some pieces of information given a solution or given the differential equation. One thing I want to mention, so P of t is the population at a given time t, M is the carrying capacity, K is the maximum population growth rate, and then the initial population is when we put in 0 for t, and then we can also find A doing this. So something to just kind of know about the logistic model is if it is growth, so kind of how M works is it doesn't just grow without bound. There's kind of this boundary that it's going to eventually hit. So kind of looks like this, where it's going to level off. And this is the line y equals m. So that's what it means by carrying capacity, is it's going to like max out. There's a certain value that it can never go to. And basically that's because population cannot just grow exponentially. Like we're going to run out of resources, or like if you're looking at how fast like a sickness is growing, like it can only grow as fast as the total population, right? Or it can only like spread to the total population. It can't go beyond that. And so this is when K is greater than 0. This is growth, logistic growth. And then we can also have the other direction where we start with again, a max kind of population. So that's the M, the carrying capacity, and our logistic model could represent decay when K is less than 0. So this one is decay. Okay, and one of the questions we're going to be asked occasionally, you guys, is when is the population growing the most rapidly? So if we think about that, that is when the slope is like the steepest, which is happening when the slope changes from increasing to decreasing or vice versa, i.e. an inflection point. So both the inflection points okay, and again, this is, the proof of this is in your book, but an inflection point occurs in this model when at exactly half of the carrying capacity, which is kind of interesting. Point is always at m over 2. So you can kind of see there's only that one inflection point in either situation, okay? All right, so we're going to use that later on. All right, so this first one, they're actually already giving me the solution to, they're giving me a logistic function and asking me to identify the different pieces. So remember, M is the numerator here. That is our maximum carrying capacity. So we're just picking out the different parameters. The maximum population growth is our rate K. So remember, in the equation, it's negative K. So K here is 0.36. Okay. The initial population. So this is, what is the population when time is 0? So I'm going to substitute in 0 for t. Oh, sorry, I wrote 25 there. That should be 24. We're plugging in 0 for t. Okay, so this is going to become e to the 0, which is just 1. So we have 650 over 1 plus 24 times 1, which is just 24. So we have 650 divided by 25, which gives us 26. So that means there were initially 6 individuals in this population. We don't know if it's people, we don't know if it's animals, bacteria, what it is, but there were 26 individuals at the start of this model. Okay, when is the population P, or what is the population P when it's growing the most rapidly? So again, this question is inflection points. And again, how we get that is we take the carrying capacity and divide it by 2. So our carrying capacity was 650 divided by 2 gives us 325. So the population has 325 individuals in it when it's growing the most rapidly. Okay. All right, one more example. You guys have problems just like this one in your book assignment. So the first thing is recognizing that this is a differential equation. That solution is the logistic model. So remember, this piece right here is the K. This piece right here is the M. So we are going to write it as the solution, right? Because they're asking me to solve. So the solution to a logistic differential equation always will have this form, right? M over 1 plus A e to the kt. So we are plugging in the M, which is 1200, A e to the kt, 0.03, oh, sorry. Yeah, we know K, T. What we need to solve for here is A, and we're given the initial condition, P of 0 is 25. So we are going to plug in 25 for our P of t and 0 for t to solve for A. 1 plus A e to the 0.03 times 0. So again, I get e to the 0, which is 1. So we have 1 plus 1 times A. Okay, so again, I'm trying to solve this for A. So I'm going to go ahead and multiply the 1 plus A to the other side so that I get it out of a fraction. Divide by 25 on both sides. 1200 divided by 25, I think is 48. Yes. And then subtract 1, so we get A is 47. So my solution, I'm going to put back in this form, but with all the numbers I now know. So our carrying capacity was 1200. We found A is 47. Oh, and should this be negative? Sorry, guys, this should be negative. Negative, because it's negative K in the solution. And that's fine. Negative times 0 is still 0. Okay, but we want to write it in here correctly. And then T. So now I could solve for the population at any time T, given that solution equation. And that's it for 7.5. Thanks for watching.